Okay, so to start today, I want to the focus for today will be about Markov models. But to start the lecture or to start the workshop, I want to give a simpler example. And over here, we can see that we are just trying to model the weather. So I guess you shouldn't really call this modeling for the weather, and it should be understood more like broadly. And over here, I just use like weather as example. So for example, here the weather will be either sunny, which will denote with the letter S, or cloudy, which will denote with the letter C. And one of the simplest probabilistic model that you can come up with is just that each day we just say the weather is modeled by a coin flip. And in this case, with a coin and has two sides, either S or C. So to predict the weather for tomorrow, we just flip the coin, right? If it lands on S, we'll just say, oh, tomorrow will be sunny. And if it lands on C, we'll just say tomorrow is cloudy, right? And however, this is something that is maybe it's not quite useful, right? Because for example, if let's say the weather is sunny today, I guess depending on the location, and then it's very likely for the weather for tomorrow to be sunny as well. And this is where the Markov model enters into the picture. So we introduce some kind of a dependence. The dependence is actually very simple. And you can think about the weather tomorrow depend on only on the weather today, but not the past. And then to represent the model, we're going to look at this this diagram here. This is sometimes called the transition diagram. And then this arrow starting from S just means that, so suppose given today, our weather is sunny. And with probably P here, tomorrow the weather will also be sunny. So we have this arrow here coming back to S. And then with probably 1 minus C, the weather will be cloudy tomorrow. Here you can think about P is just some number between 0 and 1. Right? And as you can imagine, if P is a number that is close to 1, that just means that if today is sunny, then it's very likely that tomorrow will also be sunny. Okay. And I guess to complete the diagram, we also have to tell people, and we have to decide also what happened when the day is cloudy, right? So out of the letter C or the state C, we have 2 more arrows, which is Q and 1 minus Q. Another way to represent this information is through something that is known as a matrix. And then we can think about that. So this matrix is, or as you can think about this more like a table. So on the vertical column here, we have the S and C. This just means that this is going to be the weather today. And over here, we're going to have the weather tomorrow. It's either going to be S or C. And this P here just represents that given that today the weather is sunny, what's the probability that tomorrow the weather is also sunny, which is again, according to a diagram, it has probability P. And the probability that we go from S to cloudy, today is sunny and tomorrow's cloudy, is going to be 1 minus P. And similarly, going from, we have a probability going from cloudy to sunny, which is will be 1 minus Q, and the weather stays cloudy will be just Q. So sometimes this matrix here is denoted by P, and this is called the transition matrix. And over here, I just want to label to put in a little bit label. So these matrices here, you should always think about these states where these letters were just hidden. So you should really just read the matrix in this way. So this is called the transition matrix. And I'll take a pause here to see if there's any questions. All right. Okay. So now what we're interested in would be some kind of a long time behavior for this Markov model, right? So now the Markov model is given here. It just tells us, so, given today is sunny, what's the probability that tomorrow will be either sunny or cloudy, and vice versa. If today is, in this case, if today is cloudy, then tomorrow will either be sunny with probability 1/2, or it stays cloudy with probability 1/2, which is 0.5, right? And one way you can think about to simulate this Markov model is that we have 2 kinds of coins. We have the red coins with 2 sides, which is given by S and C. And we have another coin, which we can call the green coin. It also has 2 sides. It's either S or C. And in this case, for the red coin, the probability that lands on S has probably 0.9. And then the red coin will land on C with probably 0.1. And as you can see, for the green coin, it's a fair coin. So the probability lands on either S or C, it's both 1/2. Right? And suppose that given that day 0, we are at, it's sunny, right? And then we want to look at what's going to be the weather. We want to simulate what's going to be the weather tomorrow at day 1. And what we can do is we can just flip this red coin, right? And then with the probably 0.9, it will land on S, which means day 1 will also be sunny. And with probably 0.1, it lands on C. It just means, okay, day 1 will be cloudy. So let me fill this in with the blue color. So this is, let's suppose that in the simulation, in this realization that, so when we flip the red coin, we get S, right? So the day 1 here is sunny as well. And then in order to continue this, to figure out the, to simulate the day 2, again, we're going to flip the red coin, right? Because over here, our day 1 is sunny. So we're going to flip the red coin again. And let's just suppose that in this case here, the coin comes with a C. So this means, okay, so the day 2 will be cloudy. So now, given that day 2 is cloudy, we also want to simulate like what's the weather for day 3. And in this case, we have to switch our coin because now day 2 is a cloudy, right? So we have to switch to the green coin, and then we're going to flip the green coin. So the outcome will either be S and C, but the probability has changed. In this case, they have equal probability. And then let's just say the coin, if we flip the green coin and it lands on S, and then the weather for day 3, we're just going to become S again. And then going from day 3 to day 4, we're going to just flip the red coin again. And in this case, let's just say it's S again, right? So, and you can think about this, it just continues like this. So a little bit later, we're going to look at a way to simulate this Markov chain. But for now, let me just offer another way of viewing this Markov chain, which makes this transition diagram sometimes called. It's more intuitive. So in this case, we can think about we have 2 sites. So they're called S or C. Right. So it's sometimes called states or 2 sites. And what we have here is a particle. So I'm going to write it in green. So let's just say, let me just fill it up. So let's say we have a green particle, and then let's say just the particle at time 0, it's at the state S. And then what happens here is that the particle will try to make a jump at each time, each day. And then the way the particle jumps is described by this diagram here. So this means if the green particle is at the state S, then when it jumps with probably 0.9, it just comes back to S itself. So you can think about it, does it move or just make a jump to S itself, or with 0.1, the particle will jump to the state C. Right. So this is just a really equivalent way of understanding this model. Okay, and then okay. So for example, the particle can the first time the particle can jump from S to itself, and then at the time 2, the particle can jump from S to C, and at time 3, the particle can jump from C back to S, and then from time 4, the particle can jump back to C, and time 5, the particle can jump, or just say stay at C. Okay. So now for this one, one of the interesting, or I guess one of the most important quantities that we want to try to figure out is the following. Let's just say given today is, or at day 0, it's a sunny day, and we want to look at this ratio. So that is, what is the number of sunny days in the next 10,000 days over here, and I want to normalize it by 10,000. So it's going to be a number between 0 and 1. Okay. Okay. All right. So let me take a pause and see if there are any questions. All right. And of course here the okay. Right. And of course the 10,000 here, you can think about this as just any large number, right? It doesn't have to be 10,000. It could be like, 20,000, etc. Okay. So I guess before we try to simulate this Markov chain, let's try to look at the following. So this is kind of a simple exercise for you guys. In this case here, we're going to try to guess what this ratio is, right? I guess you can think about this as like for fixed n, this quantity will be a random quantity, but as n gets larger and larger, and this ratio here would converge to a deterministic number, right? So converge as n gets larger, so this will become some number. And a way you can think about this is if we flip a fair coin n times, and then you can say, oh, when n gets very large, we can probably see n over 2 of, or you can think, or n over 2, many of the coin flips will be heads, and n over 2, many of the coin flips will be tails. Or you can, another way to say it is going to be like 1/2 of the coin flips will be heads, and 1/2 of the coin flips will be tails, right? So it's kind of like can be understood in this way. But in this case, it's slightly more complicated than just like flipping a coin n times and look at the outcome of the coin flip, whether it's heads or tails. And in this case here, it involves it's a Markov model instead of the independent model that we have seen at the first slide. So now we have two Markov models, right? So we have A here and B here. Okay. And I guess for the first part, maybe let's take a minute to think about these. So over here, I guess that maybe I should ask the questions is if we have to guess, like what is this limiting ratio, right? So what is the number of sunny days in the next n days from our observation or from our simulation of these Markov chains? So what would be this limiting ratio as n gets larger and larger? And it's going to be a number between 0 and 1. If you have a guess, you can put it in the chat. All right. So I see someone said 1/2. Is this 1/2 of part A or part B? Yep, 0.5. Okay, 0.5 is part A. Let's see. Okay, so maybe from symmetry, both are 1/2. Right? Yep. Okay, so maybe let's wait one more minute for people to think about this problem. Okay, so essentially, I think, yeah, as you guys said, this ratio here, the limiting ratio here would be exactly 1/2, and it's actually for both of these models. Add these in. Right. Both of these models, they're both 1/2, and you can think about somehow just from the symmetry of these models, and right, and if you actually look at A closely, the model from A is actually exactly the coin flip model, where the weather is decided by coin flip, where each time the probability is going to be 1/2 between S and C. Okay. So the next part is, so now both of these models will give us the same ratio, 1/2. But then what happens if we sample from each of these models? So what kind of outcomes would look like? So in part A here, so I kind of just like put up, I kind of just like, sketch out a simulation here. It's almost like we flip a fair coin, which has two sides, S and C. Each had, and then I just flip the coin over and over and over, and then we're going to see a sequence of results like this. But however, for part B, it's going to be a little bit different. So if you guys had to guess what would a sample from the second model would look like, I'll have you guys think about this, and then you can just type in like, a sequence of S and C's to can kind of represent like what would the outcome from the second model would look like. I'll wait another minute. So essentially, of course, there's no correct answer because it's a guess, but I just want to see, or I just want you to have to think about is what is the difference between the outcome of the model A and outcome of the model B? I already see some great answers. And also when you're typing out answers, feel free to share with everyone instead of just send it to the host and panelists. Right. So, okay. So in this case, we can see that, so essentially what happens here is that it's exactly like this. So we're going to see a lot of patterns. It's just going to, a lot of patterns like this. And a way you can think about it is, suppose now we put a particle here at S, then with the probability 0.99 at the next time step, it's just going to return at S, right? So it's just going to be keep on, jump and return in S and jump and return in S, just like this. And finally, it will make a jump to C. This is a small probability it will jump to C. And then what happens here is that the particle will just going to be continuing staying at C at each of the next few time steps. So we kind of see like the sequence of continuous C, the letter C's, and then I'll switch back to S. All right. Okay, so now I guess it's time for me to show a simulation. Okay, so can everyone see the screen? Okay, great. Okay, so over here, we're just going to try to simulate this Markov chain. In this case, we have the two states. It's either sunny or cloudy, right? S and C. And the S days will count the number of sunny days, and the C day counts the number of cloudy days. And initially, let's assume that over here, the MC starts for a Markov chain. And another way you can think about is the particle that we have drawn. So we start with at the time 0, we have a particle at S, right? And this is essentially the Markov chain. So the n here, n is going to be the time step. We'll go from 1 to over here. I had 2,000. It doesn't really matter. I can do like something like 9,000 or something like this, and then we can change this part. This is going to be the number of days we observe. Okay, let's do 10,000. It might take a little bit to run, but okay. Anyways, okay. So now we want to see what happened to the next day, given today is sunny. Or another way to say it, the particle is at the site S, right? So if we see that the particle is at site S, then as we mentioned before, we're going to flip a coin, right? And then the flip a coin can be done using the phone, right? This is the random number function, and this is something that we've seen a couple of weeks ago from Kishat. And what it does is just going to produce a number between 0 and 1 uniformly, right? And in this case here, if we pick a number uniformly from 0 to 1, and then we just want to say if in the case that is less than 0.9, right? And of course, this event happens with probably 0.9. And then we're going to say the Markov chain is going to stay at S. And then what happened to the S day, the counting of the S day is just going to be S day will be the original S day or the old S day, and then we'll just add 1 to it. And or else This just means the random number that we have generated uniform from 0 to 1 is more than 0.9. And then we're just going to say the Markov chain will jump from S to C. And in this case, the cloudy day is going to be the total number of cloudy day. We'll just add 1 to it. Okay, and this is the case if currently the particle is at S. You can think again we flip a coin, which with probably 0.9 we're going to stay at S, and then with probably 0.1 we jump to C. And now what happened to the if we're currently at a cloudy day, and then this is just this else corresponds to this part of the if statement. This just means okay, so now our Markov chain is really at C, and again over here we're going to flip a coin. Now in this case will be probably a half and half. So this just means if the random number from 0, 1 is less than 0.5, we're going to jump to S, and then the total number of sunny days is going to be we're going to add 1 to it. And on the other hand, with probably half, the particle is going to stay at C, and then we just add 1 to the total number of cloudy days. And in the end, what we're interested, I guess, is really this ratio, right? So the number of sunny days over the total number of days. Well, in this case, we can just add the cloudy days and sunny days. This is going to be like the 10,000 from our previous slide. And of course, here we can also look at the ratio of the cloudy days, but then there's a simple relation between the two, right? Because they add up to these two ratios add up to 1. So knowing one of them would be enough to see this. Okay, so now let's try to run this, and then I want to output the percent. Oh, let's see, percent. Okay, sorry for the typo. Okay, so in this case here, the first entry here is 0.8370. Okay, and then so let me actually write it on my next slide, so we'll see here. So 0.8370. Okay, and we see that this is quite close to 1. Okay, so now I'll come back to the slides. I'll stop sharing here, and all right. So now this is a number that we just saw from the simulation, right? So when I think about this, is just like the limiting ratio, right? The number of sunny days in the next n days divided by n, where n is some large number, and we can think about in one of our simulations, the outcome is just going to be 0.8370. So next, I guess what we're going to try to do is we're going to connect this number here to our transition matrix that we have defined at the beginning. Just recall the transition matrix for this model here. It's over here. And so I'll talk about matrix multiplication wide part. Sorry, part B was right. So someone asked in the chat, can you re-explain why part B was also 0.5? Oh, sure. Sorry. Okay, I guess let me bring it back. Okay, so over here, I mean, and one way to think about it's also 1/2. It's like an intuitive way to think about is there's a symmetry between the two, right? So you can think about what happens. We can split the model into this part. So this just says if currently we're at the state S with probably 0.99, we'll just stay at S. And then with probably 0.1, we're going to jump to some other state, in this case, C. And for the other side, it's just going to be this, right? So this just says if we are at C, and then again, with just the same probability 0.99, we're going to stay at C. And then with the same small probability 0.1, we're going to jump to S. And right, so there's like a symmetry going on. And another way you can think about this is when we're doing the simulation here, we had these two kind of, we essentially use like these kind of two coins, right? And in this case here, you can think that we have, let's say again, a red coin with 2 different sides, and we have a green coin with 2 different sides. I'll just use this black color. So the red coin has S or C, and then the green coin will also has S or C. So depending on which states we're currently in, we're going to flip either the red coin or the green coin. And the red coin, the probability that it lands on S will be 0.99, and lands on C, this probably was 0.01. And then for the green coin, it lands on C with 0.99 and then 0.01, right? So you can think about they are essentially kind of like the same coin. So there's like a symmetry between the 2 cases, and that's why the limiting ratio here is, again, it's going to be a half. Okay. Oh, sorry, we're over here. Oh, okay, so hopefully that. And of course, again, this is just kind of a guess. I didn't really do a computation for this. It's just going to be kind of a intuition here. Okay. All right. So now back to the transition matrix. And something interesting we can see here is that if we raise this transition matrix to a high power, in this case, in this case, I guess k here doesn't even have to be that large. If we just do a k is like to 50, then this matrix here is going to be approximately equal to this value here, and we can see that this number, the numbers in the first column here, they're equal. But then also another thing to notice is it's quite close to this number. And in our simulation here, with the n we chose was 10,000, right? And if we increase n further and further, and essentially the number that we get from our simulation will exactly be it will be closer and closer to this 0.8333. Right? And another way to say this, we can think about this is just going to be the number in the first column here represents this ratio, which is the number of sunny days and days divided by n, and then the number in the second column here is going to be the number of cloudy days in the first n days, in the next n days, normalized by n. Okay. Oh, and maybe I should talk a little bit about the matrix multiplication. We're just raising a matrix to the kth power. So I guess it's not really something that is covered in high school. So for matrix multiplication, in this case, the example I had was just, in the first matrix, the entries are A, B, C, D, and then I'm going to multiply the second matrix. The entries will be 1, 2, 3, 4, and then this is just going to be the matrix multiplication we're trying to figure out. And one of the easiest way to write down actually to compute the matrix multiplication is going to be, I'm going to write the first matrix here, over here, and we're going to write the second matrix over here. It's not next to it, but it's actually on top. And what happens here is we're going to do some computation to this matrix here, and this matrix here is going to be the resulting product over here. And then the way we can do this is just going to be so for example, for the first entry here at the star, so it's just going to be a 2 by 2 matrix that has four numbers in it. So for the number star, it's going to be generated by the first row of this matrix and the first column of this matrix. And then to get the star, it's almost kind of like I don't know if something it's probably from geometry, it's called the dot product, right? If you or inner product. And in this case, what we can do is we're going to look at the first entry here and then multiply the first entries here, which is give us the A times 1. And then we're going to do the second entries B times 3, which is over here, and then we're just going to add them. And this will give us the resulting entries here at star. Okay, and maybe just as an exercise, if we put a triangle here, so can you guys write down what would be the the expression for the triangle in terms of the A, B, C, D's and 1, 2, 3, 4. So in this case, I should think you can think about it's created by this this second row here and the second column here, and then that'll be right. Exactly. In this case, it would be 2 times C plus 4 times D. Right? Yeah. And once we know how to do the matrix multiplication, then the raising, for example, raising a matrix of power, you essentially just do the multiplications over and over again, just like for the numbers. Okay. So now the next question, maybe I'll just try to give you some kind of intuition, is just that why, when we raise this transition matrix to a large power, type of large power, somehow we get this ratio, right? Because it seems like the two are not really connected. And to do this, we have to look at the problem with another point of view, which is going to be given by the first equality, which is going to describe over here. And I said over here is not quite, it's quite non-trivial, the equality, to see they're the same. So what this says is that if we look at the number of days in the next n days, which are sunny, and then we normalize by this n, this is going to be the same as the probability that if we just look at the nth day, and that day is a sunny day. Right? So you see there's a difference between the two. So in the first one, we would need so we're looking at the entire outcomes, the weather of all the day from day 1 to day n, and then we count the number of s in the next n days, and when you divide it by n, then we look at the ratio. And the second part here is that we're just going to fix some large n, and then that day will either be sunny or cloudy, and then we just look at the probability of that day, whether it's sunny or cloudy. Will this presentation be goes in? Yes. So yes, we'll add the presentation to the Google Drive. Okay. And yeah, so now maybe for the equality is quite non-trivial, but hopefully I can convince you that if one of these number is close to 1, and the other one should also be close to 1, right? So you can imagine in the first case, if let's say if the ratio here is really close to 1, this just means in the next n days, we'll see a lot of sunny days, right? So there will be just very few cloudy days. There we'll see a lot of letter S. And then you can think about that. It kind of indicates that if we just look at the probability of some, like the nth day, some day that is far in the future, it will also more likely for it to be sunny instead of cloudy, right? So you can kind of get a feeling if one of them is close to 1, then the other one should also be close to 1. And if one of them is close to 0, and the other one should also be close to 0, right? And so now once we have this equality, and then the next part is that to compute the probability that the nth day is either sunny or cloudy, it's essentially given by raising the transition matrix to the nth power, and the n here would match. Okay, one can essentially obtain the information from there. And okay, so for the next part, we'll try to see why this is the case. Okay. So for this, let's say given that day 0 is a sunny, right? So we always start with a sunny day, and in this case here, we'll define this is so-called a horizontal vector. You can think about it as kind of just a bracket with 2 numbers in it. Another way to think about this is just going to be a special matrix. Before we had a 2 by 2 matrix, and in this case, it's going to be a 1 by 2 matrix. And then the I here just stands for initial condition. This is what the letter I means. And then it's 1 and 0. It just means the probability that the day 0 is sunny is going to be 1, because that's just something we assume, right? We assume day 0 is sunny. And then the second entry here just means the probability that day 0 is cloudy. This will be 0. Again, just come from our assumption. And let me think. Oh, sorry. So someone asked, can we think of this equality as a frequency interpretation of probability. Yeah, that's actually a good idea. I never thought about it because like yeah, I would definitely see it makes sense, right? Because how do you see these two quantities are close are related to each other? Yeah, that's a really good question. And yeah, I would agree. Yeah. Okay. Right. And in this case here, let's see. So yeah, so this is day 0. And so for the next part, I would like you guys to try is that, so now what is the probability that the day 1 is gonna be sunny, given that day 0 is sunny? So I would like, if I'll give you guys maybe a few seconds to think about this, and then you can just write your answer in the chat. Oh, maybe I should say again, it's from the same model that we have seen before. Maybe I'll add it here. So we have S and C. This is 0.9. This is 0.1. This should be useful. 0.5, and this is 0.5. Right. So I already see some great answers in the chat. Right. It's exactly 0.9. Right. It's kind of like from the definition of our model. If day 1 is sunny, then the probability that we're going to state the day 2, sorry, probably day 0. If day 0 is sunny, then day 1 is sunny as well. It's going to have probability 0.9. But in this case, I want to write it in somewhat of a special form. I want to write as the product of I with the matrix P. And this just means I have 1, 0 times the matrix, which is 0.9, 0.1, 0.5, 0.5. Right. And you know, to figure out the matrix multiplication again, maybe let me shift this upward a little bit, just like before. I want to put it over here, and then our answer will be over here. So again, the outcome will be a 1/2 special matrix, and the first entries here is going to be obtained by this row and this column. And we can easily see that this one is going to be 1 times 0.9 plus 0 times 0.5, right? 1 times 0.9 plus 0 times 0.5, right? Just from the previous exercise we did on the matrix multiplication. So this is just 0.9. And on the other hand, well, this one is just going to be 0.1, right? Erase this. Then also add in the remark over here. This is the probability that day 1 is sunny, and the second entry here is the probability that day 2 is cloudy. Sorry, day 1 is cloudy. Sorry. Right. And then just follows directly from our model is going to be 0.9 and 0.1. So now for the next part, another exercise. So what would be the probability that day 2 is sunny? And maybe I'll give you guys a couple of minutes to think about this. And I guess as a hint, you know, there will be 2 different situations, right? The first is that, for example, when the day 0 is sunny, day 1 is sunny, and day 2 is sunny. And it could also be day 0 is sunny, day 2 is cloudy, and sorry, day 1 is cloudy, and day 2 is sunny again, right? So this is just something I can show here. So there are 2 situations. Either we can observe just SSS, or SCS, right? In both of the cases, so this is whether day 2. This is day 2. And this is day 0, day 1, day 2. And it could happen in this in both ways. And so what will be the probability that day 2 is sunny? Mm-hmm. Yeah. So again, if you like, you can feel free to share your answer with all everyone in the workshop. So I think by default, all your chats will be sent to hosts and panelists instead of everyone. Yeah, I see. Yeah, I see a lot of great answers. Okay, right. So I think they all look great. So so the way we can compute this this probability is that well, let's first compute the probability that we get S, S, and S. And in this case, what we can imagine is that we're going to flip 2 red coins, and they both land up heads, right? So recall we have the red coins, right? So okay, let me just go to color red. So we have these red coins. So that it has 2 sides, S or C, and it lands on S with probably 0.9, and it lands on C with probably 0.1, right? And in the case of S, S, and S, we will need to flip. Essentially, we flip the coin twice, and then both of the results are S, right? So the twice is because over here you can think about this is the coin flip, which decides the second is also S, and then a second flip will decide, it's kind of deciding between this pair and this pair. So we have to flip the red coin twice. And the probability for this is just going to be 0.9 times 0.9, right? It just means we flip it twice, and in both times it lands in S. And on the other hand, so for this one, so okay, so the S and C would represent we're going to flip a red coin. This is going to be our first flip, and it landed on the side with the letter C, right? So this means we go from sunny to C. So this happens with probably 0.1. And then next, for the second coin flip, in this case, we will have to flip the green coin because we're currently on the side or on the state C, which means that's a cloudy day. So in this case, we have to flip the green coin. Just recall for the green coin, we have these probabilities. So green coin, it also has 2 sides, S and C, each with a probability a half. Right? And in this case here, it just means the second bracket here just means we flip the green coin and it lands on S. So it has probably 0.5. Right? And of course, either one of these cases could happen. So we're just going to add them. And you can see that in this case, the outcome will be 0.86. Sorry, it's 0.81 plus 0.05. It's 86. So this is going to be the probability that day 2 is sunny. Okay, and we can see that we did see something similar, closely related to this, right? It's kind of like an entry from the matrix product that we have seen before. And in this case, we see that this is the entry is exactly from the following. If we do the initial condition I times p squared, and then the entry here, the first entry will just be exactly 0.86, and then the second entry will be 0.14. Well, we know the second entry is because they add up to 1, right? Because it's and okay, so maybe let me expand out this a little bit. First, let's try to compute p squared. And then you'll see that when we're doing the p squared, we get exactly this type of computation show up. So the p here is just this is 0.9, 0.1, 0.5, 0.5. Right. And the reason, okay, I guess, yeah. So the matrix product is associative, right? So instead of I times P times P, we could do just P squared times I. So 0.9, 0.1, 0.5, 0.5. Right. Now for this matrix squares, for this P square, let's just calculate the first entry, which is given by the first row here and the first column here, right? And in this case here, we see that this is exactly the same computation is 0.86, which is something that we have computed over here. Okay. And then what I does is just says, oh, we're going to look at the first entries. Okay. All right. So, and then this kind of just demonstrate the probability of we're asking if, let's say, the day instead of 2, if I replace it with a k, and then we're just going to instead of change the p squared to p to the kth power. So that's essentially the relation. Okay. So next, okay, let's see, we're almost out of time. So for the next part, we want to look at so now suppose to do things in reverse, right? In the previous part, we were given a Markov model, and then we found out its long time behavior. And in this case, suppose we have some kind of a data set, right? So let's say we observe the weather for 10,000 days. Let's say 8,000 of these days were S and 2,000 of these days were C. So it's kind of data set like this. So how do we come up with a Markov model? Right? How do we determine the probability P and Q for which essentially the particle jumps? Okay. And this is essentially done given this is so-called the Metropolis Hastings algorithm. Sometimes it's a special kind of a sampling algorithm from what's known as a Markov chain Monte Carlo. And in this case, we can think about we have a target. Our target is the following vector, because from our observation, we assume that we have out of the from observing the weather from 10,000 days, 8,000 of these days will be sunny, and 2,000 of these days will be cloudy. Right, from this, and then we were going to try to construct back the transition matrix P. And this is essentially the formula below. So let me explain the formula here. And also kind of, I want to write this formula in somewhat of a general setting. So instead of, so in our case here, you can imagine the index K here, K is 2 in the weather model. Right, but I just want to instead of 2 here, I want to give some of the general formula. So suppose now in this again, we're going to have some target, and we call this pi. Okay, and to do this, we can start from any transition matrix, which is given by in this case here, it's going to be a k by k matrix, and it will have some entries, and then we require the row sum to add up to 1. So each row here would add up, all the entries here would add up to 1, just like the in the special case in our transition matrix. And of course, in all the entries here, they all have the non-negative. And another additional assumption maybe we might put is that we don't want to be at the identity matrix. That just means we don't want this matrix here with 1 on the diagonal and a 0 else, right? So so this is a bad choice. So once we start with this matrix P here, and then we can define this another new matrix P. And in this case, the formula will be just given by identifying the off-diagonal entries. So this is the green triangle. So the entries of these new Pij is going to be the old Pij times the minimum of pi j. Okay, I'll just have you read this ratio. So essentially what's important is that these Pij, Pji, and the pi j, pi I, so these were all given to us, right? Because all the pi I and pi j's, we can read them off from this vector. And all the Pij here, they are just contained in the initial matrix that we had. And this is just going to be for when I is not equal to j. And then next, we want to, once we have all the off-diagonal entries, then the diagonal entries are going to just be 1 minus all the other entries from the same row, because they need to add up to 1. Right? So it's just going to be 1 minus this. So so for the last part, So this will just going to be, in our case, in our weather model. So if we start, if this is our target, if this is our target, and if we start from this matrix, initial matrix P, and I just translate them to this table here, and then P1, pi1, pi2 are given, and P11, P12, P21, P22, they were all given. And in this case, we can actually compute the two off-diagonal entries, which is 0.1, it's over here. And then the other off-diagonal entry is the 0.4, which is over here. And this will give us the off-diagonal entries, and then the diagonal entries will just be 1 minus 0.1 and 1 minus 0.4. Right. Okay. And let's see. So okay. Right. I guess let me switch to the. Let me share. Actually, share my screen here. Let's look at the simulation. So hopefully everyone can see the simulation here. So now this is just going to be this part. So we can finish over here. So this is exactly as before. So our new target, so I'll call this a new pi. It's going to be 8,000 divided by 10,000, 2,000 divided by 10,000. And we would start with this the transition matrix that we had before, which is just going to be P. And in this case here, using the formula, we're going to define the two off-diagonal entries, Q. I call them Q and T. So our new matrix here is going to be over the form. The first line will be 1 minus Q, Q, T, and 1 minus T. And okay, so let me just run this section. So we can output the new P. So now our new matrix is going to look like the following. So it would have the entries transition probability 0.9, 0.1, 0.4, and 0.6, right? And to check that this is actually the correct, the transition, the correct P and Q, what we can do is, we can simply do is we can just try to raise P, or this new matrix that we found, to a large power, and its entry should match our target, right? So if we raise this, let's say this new P, that's to the 100th power, right? And then this one over here, the entries in the first column would be 0.8, which matches our target, right? So it just means in the next 10,000 days, the number of sunny days will be exact 8,000, and the number of cloudy days will be 2,000.
So this is the problem that we're going to be looking at. If you click on that first link, we can read the problem description. I'll just go through it really quickly. The idea is that the Food and Agriculture Organizations of the UN notices that approximately 1/3 of all food produced in the world for human consumption goes uneaten. As an example, perfectly good produce that is considered misshapen or otherwise unattractive is regularly discarded before reaching your grocery store shelves. The problem is even more pronounced in the United States, where the EPA estimates that more food reaches landfills and incinerators than any other single material in the trash. This, of course, is a problem because it wastes resources, water, fertilizer, pesticides, etc. And at the same time, it seems like a bigger issue because we have the problem of food insecure people around the world. In particular, 42 million Americans are food insecure. And it seems that when we're wasting food, yet people don't have enough food, there's some imbalance there. And that is what is at the crux of this problem. So I guess I skipped over that. This is then the slide. So the first problem asks us to create a mathematical model that a state could use to determine if it could feed its food insecure population using the food that is wasted in that state. It asks us to specifically demonstrate how our model works in Texas. And it notes that you may choose to use the provided data. So let's go and look at that. That would be the second link that I sent you in the chat. And we're provided with 4 different tables. Let's just go over them quickly so we know what kind of things we have the options of working with. The first one is Texas food data. It explicitly states that this data will be used in question 1. and it tells us what is on each tab. First is the information about food insecurity in Texas. The second is the information about food loss and food waste in North America. And the third is the food produced in Texas. So I'm going to go ahead and pull that up. So that is this right here. As we saw, the first tab has information about food insecurity in Texas. We see that we have a population from 2015 of about 27.5 million people. And of those, 4.3 million of them are considered food insecure. Another thing that we see in this table that is interesting is that there are different levels of food insecurity. There are people who are eligible for SNAP, WIC, free meals at school. If you don't know what SNAP and WIC are, maybe you know it by food stamps. There's another term usually colloquially used. Then there's, I guess, an orange category where we are eligible for WIC and reduced price school meals rather than free school meals. So still food insecure, maybe not as high risk as the red category. And then there are some yellow people. So those are people in this category may not be eligible for federal assistance, but would still benefit from having availability of extra food. So I think this is important to note that we have these different levels, and we can calculate how many people are in each category by multiplying this percentage by the total number of food insecure individuals. The next thing in this table is, of course, the percentages of food waste in North America. And it breaks it down by type of food. So we have cereals, which are like wheats and stuff, roots like potatoes, that kind of thing, fruits, veggies, meats, dairy, and all this. And it breaks it down in the assembly line where things are getting wasted. So we see that most of it gets wasted in the consumption category. So that's almost a quarter to a third of the waste of grains, fruits and veggies, fish and seafood. But there are non-negligible wastes in production, post-harvest handling and storage, processing and packaging. And maybe this isn't quite clear what this all means, but then it explains them down here. So we see that in fruits and veggies, when we say losses in production, that means mechanical damage or spillage. But in regards to animals, it will be losses due to animal death. So this is an important thing so that you're reading all of the different parts of this data, because if we say, okay, let's try to save the meat that is lost in production, well, those animals are dead. We can't really save that meat. We don't want to be doing that, right? Okay, so we have some general percentage of food lost. And then finally in this, we have the amount of money spent on each different type of food. So it's broken down into the same categories: cereals, roots, oilseeds, fruits, veggies, meat, seafood, and dairy. And we have a total amount spent on each of this. Okay, so this was hopefully just to give us an idea of this first data set. We also have a few other ones, but they're not going to be as relevant to the first problem. So in efforts of just getting us going here, let's just think about that first data set. What is, I think, important and is nicely done here is that you kind of have this high-level overview of each of your data sets, particularly when you're given multiple. It's very helpful to be able to know which data comes from which one and how each set might help you, for instance. Okay, so back to the slideshow. To remind you, we are looking to create a mathematical model to determine if we can feed the food insecure population using the food waste generated. Great. So let's hop into our little mathematical modeling flowchart. We have been given the problem up here, and now we're going to move on to our building the model stage. We'll start by defining the problem. So please, in the chat, give me some ideas of what is the problem in words other than it was directly given to you, right? How could we simplify that problem statement into a sentence or two? I'll give you a few minutes and then we can share some ideas. So hopefully we are getting some ideas written down. And while you're doing that, maybe I'll just elaborate that to come up with an initial problem definition, something that I think about is what questions are we trying to answer? Okay, I'll try to give you about 1 more minute. Thank you, Keshav, for your answer. We will, I think that was a great one to get us started. Keshav suggested that the problem that we are trying to address is whether the cost of SNAP/WIC to the state exceeds the cost of wasted food. I think that's a really great idea. And it's different than the one I came up with. So that's a good thing. And we'll see that in just a second. I want to see what other ideas we might have out there in the next 30 seconds or so. Okay, well, if you're still typing, please feel free to continue doing so. Some of the ideas that I came up with were to answer the question, how much food is being wasted in Texas each year? It can be as simple as that, right? I could break that down further if I wanted to go a little bit deeper. How many calories of food? What are the proportions of protein and fat and stuff like that, if we're really trying to delve into the nutritional needs of our food insecure people. Which leads to the second question, is how much food would be needed to feed the food insecure people? Again, it can be broken down into how many calories, how many fats, that kind of thing. And a third idea is that how much of the currently wasted food could be saved. So that, right, we are losing some amount, but some of it is lost for a good reason, right? We're not going to be able to save all of it, nor should we. These are just some kind of brainstorming questions to get us going with a problem definition. And I think that is very similar to the answer we had in the chat. What is the overall mass of wasted food compared to the mass of food required by the food insecure populations? So I like these different ideas. Keshuv's thinking about cost. One of our participants is thinking about mass. I'm thinking about calories. They're all perfectly equally valid approaches to this problem. And just to remind you, the goal is to formulate the problem statement into something that is quantifiable, like money, mass, calories. Great. Okay. With this in mind, we need some assumptions, right? This is our second part of our triangle of model building. Again, I would like to give you a few minutes, maybe 1.5, if you could come up with something. Oh, didn't mean to spoil it, but give me some assumptions in the chat. I think this maybe will be easier. There's a lot of things that we can assume about this problem. Great, maybe 30 more seconds. Please continue giving me ideas in the chat. Okay, please do continue to write your assumptions. So far, we have some really good ones, similar to ones that I came up with. Also, we see that we should assume that all the food insecure have the same dietary needs, excuse me, and same dietary restrictions. So that's something that I also agree with, that we can simplify this problem significantly by just employing some averaging argument. Also, we're not given any data about the population of food insecure, about their ages or anything like that. So it does make a lot of sense, I think, to assume that they all have equal needs. Let's see. What else did I have? Okay, so the first one was that the food waste percentages in Texas follow the national average. And I think that is, again, fair because we're given data, as you remember, on North American loss, rather than particular to Texas, but rather than, wasting a lot of time digging into Texas data, since our model should be broadly applicable, we just go ahead with the North American data. Great. And write more about dietary restrictions. We also can assume, like I was talking about in the data, that these different types of food insecure people may have different needs. So perhaps we could simplify to 3, 2, and 1 meals a day, or maybe that is too extreme. Maybe it's 10, 5, and 3 meals a week or something like that. This would be something that we could look up. We could look up, what is the average income of people in each category? And given those incomes, we can calculate, okay, and based on the average cost of a meal, see how much assistance does each level need. We have one more assumption in the chat. Right, that some food cannot be redeemed. Great. So in particularly, when we were looking at the data, I talked about how the death of animals in particular, that it just doesn't make sense to try to redeem it, right? So we can kind of break down this chart further to see which of the categories can be. Great. So it looks like we have some really good assumptions to start out with. Excuse me, something in my throat. And the next part is, what variables do we need? Once again, please, maybe a minute, maybe 2 minutes to come up with some variables. And post them in the chat if you would, as usual. Thank you for your answers so far. Maybe 30 more seconds. would be great. Okay, great. So some ideas we have from the chat are calories. I think that's a great one. I like that you even gave me a name for my variable C. That makes a lot of sense. And this could refer to the calories required per day. So someone suggested 2,000 a day, but maybe we make that negotiable so that we can feed more people or something like that. We could also care about the calories within each food group, the average number of calories. And of course, that's not fixed either, right? A potato has a different amount of calories than I'm having a hard time thinking of another tuber. Maybe are lentils? I don't know. But that kind of thing, right? A chicken and a beef have different calorie contents. So we might want to have different parameters for each of those different things. Of course, we also need to know the number of food insecure people. That's huge, right? Otherwise, how are we going to quantify that? How to feed them? And also non-perishable food, that's great. Figuring out of the food that we can save, can we last it? Okay, great. So these are ideas that I also had. It looks like we might have covered it. One more that I added was the percentage of producers, distributors, consumers willing to save their food, right? So we could maybe get some people to put their almost wasted food in a certain spot to be collected and distributed, but we can't assume that everyone's going to do that, right? So this is some maybe shrinkage factor that we have to consider. That could also be part of the point before it, the percentage of food that can be saved. How much participation are we expecting? Okay, great. Okay, then this is just your big fat reminder that your statement, assumptions, and variables should be explicitly stated. Use headers to notify your assumptions, your justifications, like we've seen when we've looked at previous successful solutions. Okay, what kind of model shall we build? So in this case, I think that just a direct computation of food wasted versus food needed is totally sufficient. We don't need to make a super complicated model if it doesn't make sense, right? So we talked about probabilistic models today. We talked about differential equations last time. And neither of these really, they could be applied, but they don't really need to be, in my opinion. So this is just a PSA that don't add unnecessary complication when you can just calculate some values and use that. Because then you can really spend more time on making your assumptions really good, making sure that the equation that you have makes sense, and comparing it to some other data. Other options that I just gave would be a statistical model, so that'd be fitting some sort of regression. It's a little tough because we weren't given any errors here, but in the next parts we will be. We could also consider an optimization problem. But like I said, I kind of am leaning towards the simple model in this case. So if this were my problem, maybe what I would do is I would make one equation that says, okay, well, the question asks, what can you feed the food insecure. So maybe I just calculate all of the food wasted based on, the amount of money spent, and then somehow convert money to calories or money to mass, like we said, and then multiply by that loss percentage in each category, and then just calculating the number of calories or mass needed to feed the food insecure. If that difference is positive, then we can feed them, and if not, if it's negative, there just isn't enough wasted food to feed them, and that's a perfectly fine solution. Okay, any questions on part one? I think, okay, I guess we have one more slide about part one. So if we choose my model, if I have done a great job of convincing you that simplicity is helpful here, how do we know that this simple model is going to do well enough? Well, we can look at the data. We can see, in this case, we don't have anything to fit it to. There's not really a time series or anything like that. But we could calculate, okay, maybe in multiple ways. Maybe we calculate it one in the mass by calculating the mass of food. And then if we convert that mass back to dollars, does it still make sense using the dollars tab of our spreadsheet? That kind of thing. We can look at a sensitivity analysis. I think this will be next week, actually, or next week or 2 weeks from now. Stay tuned. That'll be some good stuff. Great. So that is all I have for part one. Are there any questions before we move on to part two? Okay, well, as always, if they come up, please feel free to chime in anytime. So part two now asks us to look at specific individuals' food waste habits. So the question states, personal choices when it comes to food consumption occur at the grocery store, school cafeteria, restaurants, and at home. Create a mathematical model that can be used to determine the amount of food waste a household generates in a year based on their traits and habits. Demonstrate how your model works by evaluating for the following households. So this is a pretty similar idea to the first problem, just kind of shifting our focus from the state of Texas to the individual household. And it is now giving us some more information about ages, about income, and asking us to incorporate that to make our very simple model a little bit more complex, a little bit more realistic. So let's see. Let's go ahead and try to define the problem. I'm probably just going to flash up my answers and then get more input on the subsequent rounds about variables and assumptions. So the question that I'm trying to answer in this problem is how much food gets wasted at the consumer level. We want this to explicitly depend on income, household size, and age of household members. It also mentions something about these decisions being made at schools and restaurants, grocery stores. So how might that influence, right? Okay. Before we start looking at variables and parameters, let me show you some of the other data that they've provided us. So going back to our nifty little summary here, the second data set that they provide us is called food expenditures. And it's kind of clear that they want us to use this data for this problem because it says helpful to gain insight on the food choices people make, right? And that's exactly, I think, almost word for word what the problem asked. So we have in the first tab, the total dollar amount of food spent at home. And then we look at the food spent at home by different outlets. So we kind of break it down from that first tab. then we will look in the third tab about food spent away from home, and then away from home by different outlets. So this will be schools, restaurants, etc. Finally, the fifth tab gives us the amount of money that we are spent by families and individuals as a percentage of disposable income. So as a percentage, say, of income. So once again, we see exactly what was stated with maybe just a little bit more information. So in a grand total, we get a grand total of dollars spent for food at home. Food at home, total expenditures. We can then look by outlet in the second tab. So this gets broken down from supermarkets, convenience stores, other stores, home delivery, and once again, a grand total. And then we can look at our food away from home. So this is broken down by hotels, recreational schools, and then finally, food away from home by outlet. Oh, there it is. Okay. So this is very similar to the last tab. We just now have it broken down into restaurants, etc. Okay, we're given even more data, so that was helpful if we want to think about the differences between eating at home and eating away from home. What is going to be really helpful is, again, helpful to gain insights on choices that people make. So now we have data split among income levels, and we have average annual expenditures. So we can look at that in our consumer behavior based on income. Okay, so I think that this sheet in particular is going to be very, very helpful. So if we look at this row, it gives us the different categories of income. And as we go down, we see the average income within that category. And based on taxes, if that's something we care about, we can break it down in the demographics. So mostly these are let's see. Mostly these are adults. Mostly these are earners rather than children under 18. I think that makes sense. Okay, I think I'm reading this wrong. So this is an example where it would be really helpful if maybe I'm not sure what this is referring to. It gives me where the data comes from. And if I click here, I can probably get more information about this data. And it would tell me exactly what each piece means. The more I look at this, I think that it's telling me that in the consumer unit, on average, it's a smaller household. So I'm thinking of consumer units as a household. And on average, if you're making less than $15,000 a year, you're gonna have a smaller household than if you're making 200K or more. Okay. Then if we scroll down, this is what I think is going to be really important. All this data here. So we see our average expenditure on food. So we're estimating that if you're making less than 15K, then you're spending almost 3.7 of that on food each year. It can get broken down into these categories that we've come to love. So cereals and bakery products. So this is now a little bit different than the cereals from the first table because we're not talking about just wheats in general. We're talking specifically, I think, in this first category anyways, cereals and bakery products. The cereal products might be more along the lines of the wheats and type of stuff. Again, something to check with the default reference. Then we look at fish and we see how much each is, how much in each category these different income levels are spending. So I think that this data, more so maybe than the first data sheet, is going to be really helpful, at least how I'm envisioning the problem. Okay. There is one more data sheet, so let's look at that. And that is the average daily intake of food. So this is now where we are finally getting some data about how much people are eating and how much we want to provide to the food insecure, or how much within each household is being consumed. So we can break it down by children and adults. We also have a lower and higher income levels, and we see how much of these different foods they're eating. And if we scroll down, we see the difference that the 185% income poverty line is the threshold between lower and upper. So we'll have to convert that maybe to an income level if we want to use these different data sets. Okay, so hopefully you are now really on board with me that we have a lot of data, and that overview like this is going to be really, really helpful for you. I would create my own even, and even type in which columns I think I want to use. I talked about I want to use this food chunk in the bottom of the consumer behavior based on income, right? And I think that's really going to help organize your process and your thinking. Okay, but to organize, of course, we also need assumptions. So let's go back to that. Recall once again that the problem that we're looking at is, how does food get wasted at the consumer level? And how can we base this on income, size of household, age? So our variables and parameters, well, some of them are just given to us, size of household, income, age, right? What other ones can you think of maybe that aren't quite so obvious from the problem statement, but you would definitely like to use? Please, I'll give you a few minutes in the chat. That'd be great. So maybe something that you can think about is if we know that our variables should include age, income, size of household, what kinds of things can we get out of that? So for instance, age, it might lead us to the caloric intake of a person. I'll give you 30 more seconds in the chat. Please do add some ideas as you think of them. No right or wrong answers. Okay, great. If you think of any while I'm talking, please do put them in. Or even as we move on, always open to feedback. So we have some great ideas in the chat. Of course, the key thing that we're trying to calculate is what is the food wasted at this level? So we could consider in the volume. Another thing that we could consider that Keisha mentioned was the percentage of meals eaten home versus away. So that will definitely depend on income, right? Or I would expect it to. And because we know that waste is different at home versus in restaurants, that's definitely going to play a key factor. So I think that's a really good one. So we also have an idea, the percentage of families with the ability to save food. I think that's a great one. Right, not everyone has a refrigerator, or if you're, if you're living in a rural area, maybe you don't have the ability to buy certain types of food, right? Maybe you are eating more meat based on where you live or something like that. I think these are great ideas. Thank you so much for your participation. So other things that I included, well, I guess we got them all. The only other thing would be the aspects of each food type that wasn't covered. So for instance, the cost. If you have a lower income, you're probably going to buy less caviar, right? Also, convenience. It's possible, I don't have the data off the top of my head, that lower income families have multiple jobs, for instance, and maybe don't have the time to cook every night. Or on the other hand, are trying to save money, so they do cook every night. So there's kind of a balance there. But it's important that we think about how those might impact. And yeah, I think that's a great point that maybe lower incomes families save as much food. They're probably not going to throw out a whole loaf of bread if, if it's a day past the expiration, whereas someone who's really affluent might do that. I think that's a really good point. And we're not given specific data on the losses based on income level, but that would be something that we could assume. Great. Again, if you feel like collaborating with non-mathematicians, I think that's a really great way to maybe do some research on what kind of data is available, right? If you just Google even, you don't have to find a social worker or anything. but you can Google, what are the differences in consumer behavior, so that you get maybe a broader picture beyond just this table of mind-blowing amount of data. Right? Okay. Assumptions. We are running a little bit low on time here, so I'm just going to go over these. We are going to assume that only the factors of age, income, and household size affect the amount of food purchased. So when we are given the data a few slides back on the families that we're supposed to calculate it for, we're only given, ages, size, and income. So to me, it makes sense that we aren't really given much more information. We don't know where they live. So it wouldn't make sense to assume that based on these people. Great. We also assume that higher income households spend more money on food. And we saw that in the consumer behavior spreadsheet. So maybe what we want to get into is how much more food. So what is the relationship exactly? It could be linear. The more money you make, you just spend proportionally that much more money on food, but probably not, because I would assume that at some point you have spent all the money on food you can and it probably levels out or something like that, right? Also, it might depend on the type of food, like we talked about on the previous slide. Okay, so a little homework exercise, of course, not mandatory, but just fun. See if you can plot this data to see what kind of relationship there is between the income level and the amount of money spent. You could do it on total food, or you could break it down into categories and see maybe it changes. Maybe as you have higher income, you buy fewer potatoes, something like that. I think those would be really interesting plots that you would definitely include in your write-up, not only to justify the assumptions, but they can even be part of your model, right? And there was, in fact, one team that did this, and they particularly looked at the proportion of income spent. So I thought this was really interesting, right? So the lower income spent relatively more on cereal than the higher income, and they were able to fit this line. And this is now when we're starting to think about doing statistical models where we could fit an R² to this and see how good this fit is. So this is also important to consider. What does the proportion spent versus the total amount spent? What are the differences? It's pretty subtle, but how does that tell us something different than the total amount, right? Okay. So again, tips, these are from a previous workshop. Tips on the model to choose. Of course, you want to be comfortable. So I spent a few minutes earlier this hour trying to sell you on a simple model. And I think that a big reason that I think this is really useful is because you're likely going to be more comfortable with it. You're not going to make silly mistakes that the judges would be able to tell. At the same time, as these problems progress, there's 3 parts, right? And they get harder and harder. So you can leave the more complicated models for the more complicated problems. And then just the balancing consideration versus the simplifying model. The more simple it is, the less realistic. So there's, of course, a balance there. In this case, I think comparing model from part 1, which was just a direct calculation, now we have some error that we can throw in. And so we're getting a little bit more mathematical, a little bit more precise maybe, or at least we have some bounds on our error. And so that's just kind of going up and up and thinking about which types of model make sense for which types of question. With just a few more minutes here, I did want to show you the third problem. So far in this workshop, we haven't really looked at the third part, but there are 3 parts of every challenge. So I think that's important that we at least think about what kinds of questions they might ask. So in the third part of the problem, it asks to think about your own community. Specifically, it says communities are starting to recognize and address opportunities associated with repurposing potentially wasted food. Think of a community you belong to and use mathematical modeling to provide insights on which strategies they should adopt to repurpose the maximal amount of food at the minimal cost. In particular, quantify the costs and benefits associated with these strategies. So if I was doing this challenge, I would be highlighting all over this thing. I would highlight quantify the costs and benefits. We want to make sure that our answer set is extremely, extremely clear. I would highlight which strategies. So this, to me, implies that I should be comparing multiple strategies. And then, of course, maximal food at minimum cost. So now, but maybe before we were only looking at calories or only looking at cost, but now we kind of have to put these together, right? And now the wording of this problem really makes me think optimization problem. So I think that would be a great way to go for this. We see that the third question is a bit more open. It doesn't give us specific data on our community. In fact, it tells us to choose our community. It could be, the whole county, or it could be, my swim club, right? It's really up to you what you feel comfortable with, what you find interesting, what you could write a good model for. So I just wanted to jot down some of those thoughts for you on problem 3. Right, what data do we have? Do we not have anymore? What kind of assumptions can we make that we weren't able to make before? So for instance, if we are looking at just our school, we know the ages, right? We can simplify that part. And we can also assume that if you're in school, you aren't making any money, right? That kind of stuff from part 2 is becoming relevant. We can incorporate it. And we can also say something about the behavior because we know these people, right? I think it's really cool in part 3 if you can apply the methods from part 1 and part 2. If you come up with a totally different model, of course, that's totally fine. But it would speak to the power of your earlier parts if you were able to somehow modify them or build on them. And then finally, we are asked to compare multiple strategies. Okay, and with that, I am just up to the hour mark. I want to thank you all so much for being here. Thank you for your attention and your participation, and we will see you next week.